Good afternoon, CS109. How are you guys doing today? Fantastic. That's what I like to hear. Oh, we have another wonderful class. We get to learn about another incredible, beautiful natural phenomena that's going to allow you to solve some interesting, cool problems in the real world. So we're both going to just see something beautiful, and we're going to learn something useful, which makes for a wonderful class. Stay tuned, and we will learn about Poisson, but not the fish kind, the probability kind. At the end of today's lecture, we are going to pull some data from the HERDAT database, which is the US database of all known hurricanes in the Atlantic, and we'll try and answer questions about what's the probability of extreme weather events that we may be seeing more of. But before we get into that, it is important that you know what we're building upon. We are in this wonderful part of CS109 where we are learning about random variables. And random variables are like a gift to you by previous mathematicians. In random variable world, a mathematician will come up with a narrative, do a lot of math for that narrative, package it all together into this wonderful package of a random variable, and then if you recognize that narrative in a real world problem, you can inherit all the mathematics that is given to you. A random variable, though, at the end of the day is a very simple thing. It's just a variable which takes on values probabilistically, has semantic meaning. We've been talking about discrete random variables, and the most important thing for a discrete random variable is the relationship between the values it can take on and the probability of those values. And we have talked about a couple summary statistics, like expectation, and then last class we talked about variance and standard deviation. One of the most useful ones we've seen so far started with this narrative of, let's say we had n coin flips, and every coin flip had a probability p of coming up heads. Could we package all the mathematics for talking about the probability of exactly k heads out of those n coin flips? And we did that packaging of the math, and then we realized that, like, oh my gosh, this is so useful. We could use it for any story where you have independent trials and you want to count the number of successes in those independent trials, where they each have the same probability p of success. We introduce our first classic random variable, the binomial distribution. And as soon as you see a story that fits that coin flip one, you just say, you know my random variable is not any random variable. It's a super special one called a binomial random variable. And you have to give the parameters n and p. How many trials are there in your narrative, and what's the probability of success in each trial? And then you automatically inherit all of this for free. You inherit the probability mass function. You don't have to derive this from scratch, which is good because that saves you some time. That probability mass function can be expressed either as an equation or it can be expressed as a graph. Any way that you can give the relationship between values and probabilities that they take on, fair game. You could give somebody a function if you're SciPy stats. We are going to start building up these cards of these classic random variables. This is from the course reader. So we now have the card for the binomial. We have the card for also a simpler one, a Bernoulli. It's like a binomial where you just have one coin flip. Good times. If you know something is a binomial, you don't just get the probability mass function, you also get equations for expectation and variance, and that will be true for all the random variables that we discover. Okay. Now this isn't review that we've covered, but it's just something that we're going to use in today's class, which is this definition of the natural exponent. And I'm just going to put this on the board, and we're going to see if you can find a place in class when you can use it. And you're wondering, like, wow, that's a very beautiful limit. I wonder who came up with it. The same person who discovered the binomial. Wow, what a time to be alive. He did a lot of math. Just like us. Okay, and that's what we have for review before we get into today's great topic. Okay, I have a story for you. I would like us to think about a scenario and the probability that underlies it. And the scenario I'd like to think about is algorithmic ride sharing. You know, if you've ever gotten a shared Lyft ride, for example, there's a lot of probability that goes on under the hood to make a decision under uncertainty as who should go into which cars. And it turns out there's this beautiful natural phenomena which is occurring underneath the hood that makes this math pretty reasonable to do. So I want us to think about a scenario. So I once lived here. Oh, that was such a good time. Anyways, let's say I clicked I want to have a shared ride. The shared ride service now has a probability question. They have to decide, what's the probability of getting k requests within this area in the next 1 minute. And depending on that, they might figure out how much they should charge me for my ride, or they might make other decisions based off it. But there's really this core understanding of how many people are going to ask for a ride in the same 1 minute. You could tell me the average, the expectation, but that's not that useful for making decisions. Instead, I want to know what's the probability of 1 request, what's the probability of 2 requests, what's the probability of 3 requests, what's the probability of 4 requests. I'd like to know the whole probability mass function over the number of requests in 1 minute. Well, let's just constrain this problem a bit. Let's just say we're just talking about within a small area of where I made my request. And the interesting thing about these requests is that they'll be coming in over time. So over 1 minute, maybe one request comes 10 seconds later, maybe one request comes 40 seconds later, and these requests will be coming over this new dimension for us to think about, and what an interesting and deeply fascinating dimension it will become. So we don't have mathematics for this yet, but we can develop it based on what we do know so far. Now, one final piece of information, the only piece of information I have yet to give you, is that your ride-sharing app knows one piece of data. They know on average how many requests come within 1 minute to this area. It's not a lot of information to work on, but it turns out if you understand this beautiful underlying phenomena in our natural world, you can use that tiny amount of information and derive a whole bunch of meaning. Does that sound exciting or what? Shall we do this? Okay, yeah. Now, you don't have the tools for it yet, but we learned about the binomial distribution in Wednesday's class. And what we're going to do is we're going to hack that binomial distribution to come up with a hacky answer to the probability of number of requests within 1 minute. Here's my crazy hacky idea. Bear with me for a moment. I'm going to take my minute, which is continuous in all the beautiful complexity that time is continuous, and I'm going to chop it into seconds and make it discrete. I'm going to say my minute is actually 60 discrete seconds. And I'm going to do something even hackier. I'm going to say every second I either get 0 requests or 1 request. You're like, what if you get 2 requests? I'm like, no, either 0 requests or 1 request every single second. And that's really hacky. But once I've done this really crazy thing. I've taken time and I've recast it as a story of flipping coins. Because now if I want to know how many requests I get in 60 seconds, well, I'm going to flip a coin for every second. If it's heads, I get a request. If it's tails, I don't get a request. Cool narrative, right? Totally mind-bending. What a weird thing to do. But there is a problem. This coin flipping story that we now have a little bit of practice with requires 2 numbers. How many times do you flip your coin? 60. I know that one. Feeling good. And then you're like, but what's the probability of success on every coin flip? And you're like, I don't know. I'm like going on the edge of my seat. I'm making this stuff up. What is the probability of heads? Okay, I'm trying this really hacky thing here. Can you guys help me out? Can you tell me what would be a reasonable choice for the probability of success if I did this hacky thing of took a minute, broke it down to 60 seconds, and thought about the number of requests as being coin flips, the number of heads in 60 coin flips? Remember, the one piece of information I've given you is that on average, there's 5 requests per minute. Talk about it with the person next to you. Let's see if we can crack this puzzle. Help me out on my hacky solution. Okay, let's talk about it together. I can't wait to talk about it. I know you guys were just like having a nice calm day, and you're like, yeah, binomial, good times, and I throw you in the deep end, and we're like talking about time all of a sudden, and we're taking minutes and chopping them into seconds. Craziness. Before I even get into any answers, somebody's got a question. Somebody's like, what did you do? Like, what's this coin flips doing in my Uber pool? Yeah, question.
Doesn't this assume that it takes 1 second to process a request? Like, would your probability be different if you broke up the minute into like milliseconds or 10-second chunks?
You asked such a good question. If I could just paraphrase a little bit, you're like, you chose 60 seconds. Wouldn't this be pretty different if you chose different amounts of time? Yeah, that's a pretty arbitrary decision for me to have made. We're going to explore the arbitrariness of that decision. We'll try a couple different ways of breaking it up. But for now, I just thought 60 was pretty reasonable. Well, let's talk about this in a moment, though, because we could have a good conversation. You'd be like, Chris, it's not really reasonable. But first, let's see where this gets us, and then let's talk about what it's not really good for. That is a very good question, though. Why 60? I just chose it. Okay. So I wanted to model this as coin flips. Crazy way to think about this problem, but it requires me to say what's the probability of heads on every coin flip. Recall that in a binomial, the coin flips always have the same probability of heads. It's not always 0.5. It can be a different p. It's just every coin flip has the same p probability of being heads. That is one of the rules of the binomial. So there's no perfect answer here, but like, what's your best guess for what p should be to make my world consistent? 1/12. How did you get there?
5/60, so we need the expected value of coin flips via both processes to agree.
So you said 5, which conveniently is lambda, over 12, which is the same as...
Over 60.
Oh, sorry, over 60, thank you. Which is the same, I was using lambda as my symbol for the average request per second, and n is my number of coin flips. Okay, so your claim is, let's say we set p to be 5/60. Now we're going to simulate requests by having some poor person go and flip coins. And they're going to flip 60 coins, and it's a special coin that comes up heads only with a 5/60 probability. So your claim is that if you flip 60 coins, and they each have a 5/60 chance, the binomial expectation says the expected value of a binomial is p, so this number, times n, which is 60, which would be 5. Hey, that's nice and consistent. If you choose this number, your expected number of successes in 60 coin flips is going to be 5. Great. So this is wonderful. We now have everything we need to do to totally hack this problem. We can solve this problem using a binomial distribution. We're going to say every second you either get your request or you don't. So we can define a random variable, which is the number of requests in a minute. And I'm going to call it x. What a boring name. Man, I miss programming where you can get to like descriptive names. And in probability, it's just like x and y, but like whatever, we'll live with it. X is the number of requests in 1 minute. And this crazy thing I've said is that now x is modeled as coin flips. 60 coin flips. The probability of heads on any one coin flip is 5/60, and we're going to count the number of heads. Once we've done this, we inherit this formula. And it's such a funny way of writing the relationship between assignments to x and a probability. But that's what this is saying. It's saying if you put in a 0 for k, it will be telling you the probability that you get 0 requests. If you put 1 in for k, it's telling you the probability that you get 1 coin flip, which is our analogy for getting 1 request in a minute. If you put in, 60 for k, it'll tell you the probability that you got 60 requests in your minute. Whew, good business. Let's put in a concrete number. Let's put in a 3. If you put in a 3, we can substitute 60 in for n, number of coin flips, 3 in for k, that's our query, and we could put 5/60 in for p, that's the p that we chose to make this whole expectation work out. And if you did this, then you would be able to get an exact number for the probability of getting 3 requests within your minute. Great, we've solved it. We're done. Give us the next algorithmic challenge. We're ready. But there is this wonderful question. There's a lot of problems with this. It feels arbitrary. Why did I choose 60? And I think there was this deep insight in the question that was asked earlier is, if you're flipping a coin, it doesn't allow you for you to get 2 requests in the same second. Does it seem possible to get 2 requests in the same second? Yeah, Bernal Heights is a popular place. You can definitely get 2 requests in the same second. So if this isn't that good, is there a simple thing we could do to make it better? Everybody just yell it out. What would you do?
More divisions.
More divisions! Yeah, we have the power of computers at our fingertips. Why stop at 60 when we could do 60,000? I'm going to do the exact same thought experiment, but instead of doing 60 coin flips for it's still 1 minute, I'm going to do 60,000 coin flips, and every coin flip is representing whether I get a request within 1 millisecond. Now n is 60. What happens to p? Is it still 5 over 60? If it was 5 over 60, then you would be getting way more than 5 requests a minute, and that's the one piece of historical data that we're working with. What is the new p if we do 10,000? Or sorry, 60,000 rather? 5 over 60,000. Is that a bigger number or a smaller number? Okay. Smaller number, yes. So same problem, we just have more time frames and a lower probability of getting a success in time frames. But we're still solving what's the probability of different numbers of requests within a minute. There is a question.
Yes. Quick question. When we break it up into such small parts, I'm wondering if the binomial equation allows us in any way to change the probability over time, like make it more frequent or likely.
It's such a good question. It is. The binomial is a beautiful thing. It's near and dear to my heart. It does so much for me, but it doesn't change probabilities. Probabilities are constant. So in the binomial, it's always assuming that p is not changing. If you make p change, you would have to derive a new probability mass function. And it will be a more complicated one depending on how you're allowing your p to change. It would be so nice if binomial did that. And it does so much. We should appreciate it, but it doesn't do that. Good question. OK, so we need a constant p. We're going to use this constant p. OK. Once again, the number of requests within my minute, I'm going to use x. And it's now still this process of flipping coin flips. So it's like, I got a tails, I got a tails, I get a tails, I got a tails, I got a heads. That means I got a request at 5 milliseconds into my minute. And you can continue this process. And the number of heads is going to be our model for the number of requests. And now we can say that x's model is a binomial. And again, it's a binomial, but now n is 60,000, and p is going to be 5 divided by 60,000. And again, we can still ask the question, what's the probability that x takes on a value, say 3? And if you put 3 into this, you'll actually get a very similar number, but this will just be a little bit more accurate because the assumptions are better. It's less likely that you get 2 requests within the same millisecond. For that reason, this seems like just a straight improvement. But could we do better? Like what's smaller than a millisecond? An infinitely small sliver of time. We're going to go there. Are you guys ready to do this? Let's take a moment and get ready for a wonderful adventure. We are going to take the binomial to the limit. We're going to see what happens when we get smaller and smaller and smaller until we get infinitely small buckets. What a beautiful place of math for us to be. Are you guys ready? I can't even draw them. They're so small. But we can still start to write out our binomial distribution. So we can say, I still care about the number of requests. It's still 1 minute, even though we've gone into the infinity that is the amount of units of time within 1 minute. X is going to be binomial, but now there's infinite coin flips, and every coin flip has a 5 over infinity probability of being heads. Whoa. I know I'll tell you about the first person who did this. He must have been feeling crazy. He's like, you know what? I'm doing it. I'm just going to go to the edge today. And so he did. He thought, what if you took this equation and you thought about it in the limit as n goes to infinity? Notice I don't have a p. I've already substituted in 5 over n. And we're thinking about this not as 5 goes to infinity. 5 will always be constant. That's the thing. That's one thing that stayed true in this crazy thought experiment is as n goes to infinity, the number of slices. Okay, let's do this. Let's see something beautiful. You guys want to see something beautiful? Let's jump into what happens when you take this binomial and take it into the limit. Oh, where do you even start when you want to write out something like this? What I do is I start by expanding at the beginning. It's one of the many moves you can do. And expanding in this case can look like take this term and expand it. We've already looked earlier in class about what is the definition of this combinatorics. Sometimes we use that notation, but it's short for this equation. N choose k is n factorial divided by n minus k factorial times k factorial. Great. And then see this term, 1 minus lambda over n to the power of n minus k. As you know, when you subtract exponents, it's equivalent to if you had this raised to one exponent divided by this raised to another exponent. So I've simplified this term. Earlier in class, I wrote this beautiful equation on the board, and it's going to be our first hint that something truly gorgeous is going to happen. Because one of these terms here, as n goes to infinity, approaches this beautiful natural exponent to the power of negative lambda. Does anyone see that term? Is it this one? No. Is it this one?
No.
Is it this one?
Yes.
Yeah! That whole term. When n goes to infinity, that whole term is going to be a very nice e to the power of negative lambda. Now, my notation's got a little sloppy. This is now limit as n goes to infinity. Well, there's not an n there, so we're in a good place. I also did this thing where I took this term on the base, and I said it's 1. We're going into limits. That's a wild place to be. But my claim is, as n goes to infinity, that whole denominator starts to look like a constant. Let's break it down. As n goes to infinity, this starts to look like 0, because 5 divided by infinity is pretty small. And then you have 1 minus 0, and that starts to look like a 1, and 1 to raise to any power just looks like a 1. So this whole honkin' expression has become something beautiful. Okay, yay. Are we done? Is that where the beauty ends? No, we're just getting started. Okay, I'm just going to do a little bit of rearranging. When you're looking at an equation like this, you might think, I want to get all like terms together. In this case, let's take everything that's got an n in it, and let's move it to this side. And we're going to reserve this for terms that don't have n in it. And that's a convenient choice because we're thinking about the limit in terms of n. So as n goes to infinity, this is not really going to be changing. We have one last task to think about. What does this mean as n goes to infinity? You have n factorial divided by n minus k factorial, and then you also have this n to the power of k. N factorial divided by n minus k factorial is maybe something worth thinking about, and it's something that you'll see a lot in different derivations in probability. Let's put real numbers there. If I gave you 7 factorial divided by 7 minus 3 factorial, if you wrote this out, this would be like 7, 6, 5, 4, 3, 2, 1. And on the bottom, you'd have 7 minus 3 is 4, so you have 4, 3, 2, 1. And a bunch of these terms cancel out. This cancels, this cancels, this cancels, this cancels, this cancels. And you're just left with this is basically saying for loop from 7, decrementing by 1 each time until you get to this number. And you're going to be multiplying those together. So in our case, what we've got going on is we have n factorial divided by n minus k factorial, and that will look like n times n minus 1 times n minus 2. And remember, k is kind of a small number. It's like the 3 requests within the minute that we're going to be querying. So let's say that just k is 3. So n times n minus 1 times n minus 2 times n minus 3. Great. And that's covering this whole term, n factorial divided by n minus k factorial. We're still left with an n to the power of k. I feel like I have an off by 1 here. If you're subtracting off, I left 1 more here than I should have. If k was 3, you got to stop at 2. OK, the only term left here that I haven't thought about is this n to the power of k, and let's expand it. n, n, n. And this is in the case where k equals 3. I'm just doing it for demonstration purposes so that we can reason about what happens as n goes to infinity. If n is like 3, these are pretty different numbers. If n is 10, though this is like 10, 10, 10, and this is 10, 9, 8, and they start to look like a little bit more similar numbers. What if n is 100? They start to look even more similar. As n becomes infinity, this really starts to look like n times n times n divided by n times n times n. Now, this is not a rigorous class on limits. Rather, this is a class on probability, so I want you to see this beauty, and I want to give you guys the intuition for why this whole term here, as n goes to infinity, this term goes to 1. And you're like, wow. And you're left with, it's because this looks like 1. And you're left with this, and you're like, what's my next limit? And you're like, there's no more n's left in my equation. I'm done. And then you look at your equation, and tears start welling up in your eyes. You're like, it's so beautiful. I've got that 5 to the power of my query, the natural base to the power of the negative rate, that was the 5, divide my query factorial. And that's it. We have taken the binomial in the limit, and what seemed like a scary endeavor led to such a beautiful, simple equation. And this beautiful, simple equation carries so much power in it. It means if something's following this process where we think, events are coming independently over time, all you need is to know lambda. And if somebody gives you lambda, you can infer all this structure over the probability of getting 1 request, 2 requests, 3 requests, 4 requests. And this is the powerful technology that people in ride sharings can use to make interesting decisions under uncertainty. So, maybe I'll pause here for a second because that was a wild ride. Yeah?
How you got e to the power of negative lambda from the original?
Up here?
Yes.
Yes, it is from this definition of the natural exponent. So this is something that, you can look into, there's a cool Wikipedia page if you want to go deeper into why this is true. But this is just one of the lemmas that I came into class with. Yes?
The idea that the first one kind of eventually goes to n times n times n because the differences between the numbers are arbitrarily small.
Yes. Like k being a small number and n being something close to infinity means that this really looks like n times n times n as n goes to infinity. Like this -2 means nothing when it comes to infinity. Okay, good question. Okay, what a beautiful math proof. The person who first did this math proof did it in the 1800s, and it was Simon Denis Poisson, who was a French mathematician. He published his first paper at 18. He became a professor when he was 21. He published over 300 papers in his lifetime. Whew. He has this hilarious quote. He reportedly said, life is good for only 2 things, discovering mathematics and teaching mathematics. And teaching mathematics is a fun thing, discovering mathematics is a fun thing, but I don't know, Simon, I think there's a little bit more to life, but I guess to each their own. And for a celebrity lookalike, I'm going with French Martin Freeman. Because he was the first one to do this mathematics, he was the crazy individual who took the binomial to the limit for the first time. The Poisson random variable is named after him. And the Poisson random variable needs so little information as input, it's amazing. All you need to give to define a Poisson random variable is you just need to give that 5, the average number of events within one time period, and you could immediately know the probability of number of events within the time period. So we often call that parameter, that 5, the rate, and we'll use lambda for the rate. What are the values that the random variable can take on? When there were 60 seconds, when we took our minute and broke into 60 seconds, it could take on any value from 0 to 60. When we went up to 60,000, though, we were thinking about this metaphor with 60,000 coin flips. And technically, our random variable could take on any value from the range 0 to 60,000. But when we took it to the limit, what does that leave us for possible values that x can take on? Yeah, it can go really large. It can go infinitely large. So x could be 0, it could be 1, it could be 2, and it could be up to infinity. It's very unlikely to be infinity, but is defined over all of those numbers. It's a really interesting thing. We're talking about time. Time is continuous, but Poisson is a discrete random variable. It's talking about number of events. You can't have half an event. It's like somebody's like, oh, I kind of want to ride. That doesn't happen. You either want the ride and you request it or you don't. And if you define something to be a Poisson, you immediately inherit this gorgeous equation. You immediately inherit the knowledge of how you can relate number of events with the probability of getting those number of events. It's a magical thing. Okay, there's a lot of things that fit this narrative. This narrative is going to fit whenever something occurs over time, and you want to know about the number of events within a fixed time window. That's the narrative for a Poisson. There are some underlying assumptions for the Poisson. We were kind of flipping coins at an even rate. So we're assuming that our events, they're evenly distributed over your time segment. Lots of things follow this story, like number of earthquakes within 1 year, radioactive decay within the next hour, hits to a web server. All these things are counting number of events within a fixed period of time, and you can immediately inherit all this mathematics. You don't have to redefine it every time you see a story like this. The assumption is that events are arriving at a rate where there's lambda events per interval of time, and the assumption that this lambda is somehow constant over your period is not changing too much. How we got here is we did this crazy thought experiment where we took our time and split it into, in the limit, infinite subintervals. And we got the Poisson. Now, the reader, we derived the Poisson. This is what a Poisson looks like. This is a Poisson with rate of 5. So for those ride-sharing requests, we said on average there's 5 requests per minute. And with just the one piece of information, all of this structure arises. You tell me there's 5 requests per minute, and I can tell you the probability of getting 0 requests. I can tell you the probability of getting 1 request. I can tell you the probability that you'll get 12 requests. And I just needed one piece of information. How wonderful is that? There are other things that you can do with the Poisson. You can know the expectation and variance, which we'll talk about in a second. But long story short, Poisson, you just have a rate, and it gives you a whole probability mass function. And really, this is the major learning key. If somebody asks you a question, if they give you a rate, so an average number of occurrences per time interval, and they care about the probability of number of occurrences, that's your narrative that you're looking for. The one tricky thing that I'm going to point out early is people will give you a rate within one time interval, and you have to make sure that the units for that rate match the units of your probability question. So if somebody says, there's an average request per minute, and then say, what's the probability of number of requests within 1 hour? Obviously, you have to make those two match, and you just multiply your request by minutes by 60.
So from that one number, how can you know that the Poisson distribution is going to be an accurate representation of the entire probability?
This is a good question. I mean, as long as something follows the Poissonian process, then that's all. All the structure just comes because of the nature of limits in mathematics. And so the assumption here is that I'm saying that requests over my minute are just as likely to come in the first segment of the minute and the last segment of the minute. That's a pretty reasonable request, or reasonable assumption. And then you have Poisson. And you could observe it, like if they look at their logs, they would see this in their historical data. It has been shown time and time again. It's such a crazy cool thing. It's so crazy cool. Yeah, it's saying on average there's 5 requests per minute, but it's certainly saying it's possible to get 2 requests. It's possible to get 7 requests. It's possible to get 18 requests. It's just very unlikely. And so you just told me the average, and I was able to expand from that average to all the queries you might want to know, like the chance of 8 or 9 or 10. So the Poisson very much allows for more than 5 requests per time segment.
We learned about variance before.
Yeah.
And I was just wondering, how does the variance affect the act? If there's a lot of variance, I agree to be wrong.
If it's following the assumptions I said, I will tell you exactly what the variance will be. And you will be pleasantly surprised. Follow along, because this wonderful journey is not over. Shall we go look into the variance now? Because we've looked at this probability mass function. We've cried a tear about the beauty that we got just from knowing the rate, and that's not where this story ends. Oh my gosh, I did prepare to take us down that chapter, but before we go into talking about variance, can we hold that thought, and can I just do a concrete example? Okay, here's my concrete example. Real numbers. This is from major earthquakes within the Western Hemisphere. So in the Western Hemisphere, there's an average of 2.79 major earthquakes per year. That's the only information I'm going to give you, and now I'm going to ask you a probability question. What's the probability of 3 major earthquakes next year? Are you allowed to give a rate that's not a whole number? Absolutely. Your average doesn't have to be a whole number. Your query must be a whole number because it doesn't make sense to ask what's the chance of getting 2.7 major earthquakes. They're going to be a whole number of earthquakes. We have all the information we need. It's as simple as declare X to be the number of earthquakes next year. Recognize that it's a Poisson because you're asking for a number of events with an interval of time. You have to provide a rate when you declare a Poisson. You have to give that lambda, but we were told what it was, 2.79. And when you say 2.79 Poisson, you immediately inherit this graph, which says this is the chance of 0 earthquakes, 1 earthquake, 2 earthquakes, 3 earthquakes. Of course, this graph is represented by this beautiful equation. And you could just plug into this beautiful equation, what's the probability that x equals 3? So putting a 3 in for k, a 2.79 in for lambda, and then reducing. And you get that there's a 23% chance of having a major earthquake next year. It's so beautiful, it's natural to doubt it. This can't be real. There must be some huge assumption. There must be something wrong. So somebody did this research. Somebody wrote the paper which says, is the sequence of earthquakes in Southern California with aftershocks removed Poissonian? And there's two interesting things about this paper. They come to the conclusion that it is in fact Poissonian, and it's also the paper in the world with the shortest abstract. You guys want to see the abstract? How bold is that? They're just like, yes, done. Screw you, reviewer, too. Anyways, they studied the actual distribution. They're like, in fact, all of these predictions that we come from just doing pure math play out in the real world. And that math that we just solved is, in fact, the true probability of getting 3 major earthquakes. Oh my gosh, there's so many more cool things I have to tell you about Poisson. The next cool thing I have to tell you about Poisson is, in fact, because of the nature of how we derive Poisson, recall that we got the Poisson by taking the binomial and taking it into the limit. It can also do this neat other trick, which is sometimes you have a binomial distribution problem which has this n choose k, and that term can get so big that it can be hard to solve a binomial probability mass function. So a neat trick is, because the Poisson is defined by taking the binomial to a limit, if your binomial problems become so big, you can sometimes use a Poisson to approximate a binomial, if the binomial looks like it's going to the limit. You guys ready for this? Why would you do this? Well, historically, people didn't have supercomputers, so this was a really big deal if you could approximate a binomial. But there's two reasons. One, it could save you some compute power. I'm not sure we're that motivated by saving compute power. But the second one is, I really want to build this intuition of where the Poisson comes from. And by recognizing the Poisson as a process to approximate a binomial, you'll get a deeper intuition for what the Poisson is really about. Does that sound good? OK, let's do it. I have another question for you. I think this is such an interesting future that we might walk into. All the movies, images, emails, and other digital data from more than 600 smartphones could fit in this little pink drop if we figure out how to store data on DNA. And it's looking like that's a possibility. And for lots of reasons, we might want to have data that persists more than what we're able to do with hard drives right now. So let's play with this interesting scenario, and let's think about the possibility of storing data on DNA. And the interesting question for us to consider is, what's the possibility of corruption? So let's say we put all of our information onto DNA storage. What's the probability that like less than 1% of it becomes corrupt? In DNA, but also if you're thinking about a real storage device, you have a lot of things that you're storing. You have a very large string of data. In this case, we're going to imagine that we're going to put all of our information on a string of length 10 to the power of 4. So a pretty long string. The probability of corruption of any one base pair is rather small, but we would like it for very few of our base pairs to become corrupted. Now, this is a binomial. If you want to talk about the number of base pairs that get corrupted, it's like each letter in your string is a coin flip. This is the chance that it comes up heads, and we can talk about the number of corruptions, aka the number of heads, in our 10 to the 4th coin flips. And that's fine. It is a binomial. The binomial is completely correct. But now you have to do, in the binomial probability mass function, there's this term, and it's going to involve an n choose k. K might be reasonable, but n might be 10 to the power 4, and this could be a really, really unwieldy large number to compute. So if we can't just solve problems with the binomial directly, what could we do? Play Ultimate Frisbee. Go have a good day. No, we can approximate. We can approximate this with a Poisson. And why can we approximate this with a Poisson? This kind of looks like our thought experiment from the beginning of class where we took time and we broke it into 10,000 milliseconds. Those 10,000 milliseconds were n approaching infinity, and 10 to the fourth is clearly not infinity, but you're getting closer to infinity. So we could set up a Poisson that looks like this binomial. It's so backwards, because at the beginning of class we were like setting up we're setting up the binomial to look like a Poisson, and now we're doing a Poisson to look like a binomial. But so it goes. That is just the full circle of life. So I'm going to call these extreme n and p, and they arrive in many cases. And there's a few examples. For people who are early days of the internet, were often trying to figure out what to do about server crashes. And a lot of it had to do with being able to think about this probability problem. So let's revisit this problem. And let's say we couldn't solve any PMF for that binomial. So what we're going to do is we're going to come up with an approximating Poisson. This is not a Poisson process, but since that n was so close to infinity and it was a binomial getting closer to infinity, it's going to look like a Poisson. But which Poisson does it look like? We have to choose a rate. And before, you know how we chose p to be equal to lambda over n? Now we have to choose a lambda. And if you want to choose a lambda, you could use this same equation. You can say, I want the lambda that's equal to n times p. And if you think about it, n times p should give you your expected number of occurrences. And in this case, if you multiply those two numbers, it's 0.01. Now we can answer questions. We can say, what's the probability of k corruptions? For example, you can put in, what's the probability of 0 corruptions? And you're like, wait, but that leaves you with a 0 factorial. Oh my gosh, you're going to be dividing by 0. This is going to be a sad time. Run away. I don't know who did this. Is it just a definition? But there's a beautiful thing about the world. 0 factorial is not 0. It's 1. What a time to be alive. So this is actually a really good place to be because this is just equal to e to the power of negative lambda. And we just define lambda to be equal to 0.01. So this is just e to the power of negative 0.01. And it's saying the chance of 0 corruptions is actually 0.99. So if you had this corruption rate, you could say, oh, I feel rather confident that I probably won't get a single corruption. And this could be a reasonable way to store data. Whew, crazy thing to do. Now, I need to give you guys some guardrails, because with such great power comes such great responsibility, right? You need to know when you can use this approximation. You have to do it when n times p is moderate. So I'm going to define moderate to be any of thing that satisfies these two rules. And it's supposed to be useful when n goes to infinity, but 100 turns out to be close enough to infinity for this to work pretty well. Let me just show you what I mean by that. Here's a binomial with n is 10 and p is 0.3. That's the red bar. The green bar is certainly not infinity, it's n 100. Is 100 infinity? No. But both of these are approaching a Poisson of 3, because if you took your n times p, you would get a 3. And look how similar that Poisson is to both of these binomials. Even when n is very far from infinity, when you get this value of n being much larger than p, you have very small p, you have kind of moderately large n, the Poisson actually looks like a really good approximation. Now, for these small numbers, you can do the binomial exactly. But this is just to show you that, if your n is probably higher than 100 and your p is a small number, certainly you're going to get an incredible approximation with a Poisson. Again, what are our learning goals here? It's a new trick. It's a tool. You can use it. And also, it's to help reinforce this connection between the binomial and the Poisson, because that's just a beautiful thing. OK, and then we have a new major key, Poisson. You can use it to approximate a binomial when n is large and p is small. Now it's time for some tender moments with the Poisson. As you recall, moments is the really fancy term for expectation and variance. The expectation is called the first moment, and the variance is the second central moment. Yes?
Why do we need the assumption that NP is moderate?
Good question. I think it really is one way of expressing that you want p to be small and n to be large. And I guess,
It seems to just follow from those things.
yeah, if n was large, so like what if n was large and p was large? I think if n is large and p is large, it actually does lead to some weirdness where it doesn't actually work out. So, so
Are we like defining p as like lambda over n?
oh, well, if lambda is a moderate number, and if we're defining it, then you're fine. So we defined lambda to be, we got this p when we were approximating the Poisson with a binomial, but now we're approximating the binomial Poisson. Somebody could throw a binomial at you where the lambda is not reasonable, where it's a very different number. Okay, someone asked the wonderful question, what about variance? Like, what if your events have high variance? Like, what's going on with the variance of this Poisson? And does it ever start to break? And I have such a beautiful piece of information to share with you. Recall for the binomial, we have the expectation of a binomial, and that's just n times p. So if somebody gives you a binomial and they say, give me the expectation, you just have to multiply those two parameters together. If somebody gives you a binomial and they ask for the variance, you multiply your two parameters together and then you multiply it times 1 times p, and then you give them back the variance. We have to think about what expectation and variance should be for a Poisson. So let's imagine we have our lambda, and lambda really comes from an n times p where n is going to infinity and p is going till 0. Are you guys ready for this? Is beautiful. Lambda is our one parameter, and the expectation of our random variable, because it's a binomial and the expectation of binomial is n times p, in the limit, this n times p is just how we define lambda. So in the limit, the expectation is just your rate. And you're like, wait, no, that actually just kind of makes sense. You told me that the average number of events per time frame was lambda, and now you're telling me that the average number of events per time period is lambda. That's actually just kind of circular. Like, okay, that's just fine. But wait for this one. What's the variance of this random variable? Well, here's the variance of your binomial. And of course, the Poisson approximates the binomial, or it's the binomial in the limit. N times p, that's how we define lambda. And what about when p goes to 0 as n goes to infinity? What's 1 minus p? That's just 1. And you're like, the variance is also lambda. Everything about this Poisson is lambda. The expectation lambda, the variance is lambda. And you're like, what if your number of events is 100 per time frame? Variance is 100. If it's 1,000, variance is 1,000. It's always given to you. You give me the rate, and I can tell you the variance. And in fact, the variance is equal to exactly the rate. What a gorgeous, beautiful world we live in. So yes, I have such great news for you. Expectation and variance of Poisson are in fact the same, and they're in fact lambda. Yes?
Does this function for like all Poissons, or is this just specifically when Poisson is being used to approximate binomial?
All Poisson. Sorry, this is back to the general Poisson. So even if you're just using a natural Poisson, these are your expectation and variance. Wild. Somebody's like, I just can't believe it. This is just so mind-bending. Okay, brings a tear to my eye. Okay, this is just a random aside. This is a real license plate that I saw at Stanford. Poisson of 3, and I imagine it's just somebody who realized that with a rate of 3, they actually had a Poisson, and it brought a tear to their eye, and then they got a vanity plate. And I wish I had that vanity plate, but I don't, and that's not important right now. Okay. Now, the only thing that's giving us angst is it feels like there was a lot of assumptions that must be made for the Poisson to occur. We said as long as a process occurs with a relatively fixed rate, you'll get Poisson. And I have good news. Let's say you make that assumption about that, what we call the Poisson process assumption, that your rate's not changing, and that the occurrence of one event's not changing the probability of another event occurring. Even if you start to break those assumptions, the Poisson still ends up being incredibly good. And so there's this whole idea of the Poisson paradox, and you just think of Poisson being like the most chill random variable. You're like, I've got a rate, and then somebody's like, well, is it a Poisson process? Is your lambda constant over time? And you're like, kinda. And you're like, well, does it fit the coin flip metaphor where like one coin flip's not really changing the chance of another one? You're like, kinda, but you know, like maybe somebody requested and they tell their friend and then their friend requests it because they're going to the same place. And Poisson's chill. They're like, yeah, you've kind of violated my assumptions, but you know what? I'm still gonna give you a great probability anyways. So you can still apply a Poisson approximation when successes are not entirely independent like coin flips in a binomial, and when there's a small variation in the probability of success over your time frame. It's just that amazing. Okay, let's do a couple examples before we jump into thinking about something more interesting, like the probability of extreme weather. Okay, this is one for you guys to do. I've been talking a lot about Poisson. You guys know it's a cool thing now, but do you have the power of the Poisson yourselves? So this is what a Poisson problem could look like. See if you can figure it. I'm going to give you guys 2 minutes to think about it. Think about it first for a little bit, but please, please do make a friend and talk to the person next to you. Okay. Fantastic. Nothing in this problem says Poisson explicitly, but this problem screams Poisson now that we are educated people. So the reason that this screams Poisson is a few reasons. We're talking about the number of events happening within a time period. So we're saying number of hits to a server within 1 second. Can a Poisson apply to 1 second? Absolutely. You can apply to a year, you can apply to a second, apply to a minute. You know, you could take a second and break into infinitely many subsections just like you could do a minute. So for this reason, the Poisson seems like it'll be a great thing to use in this case. The only thing you would need if you wanted to use a Poisson is you need to know the average number of events per time frame, and huzzah, here it is. In the past, server load averages 2 hits per second. And as we now know, as soon as somebody gives you a narrative that fits the Poisson and they give you a rate, you immediately inherit expectation and variance and the full probability mass function, which means you could ask questions like, what's the probability that x equals 0? Now, of course, the one interesting thing here is this isn't asking the probability that x equals 0. It's asking the probability that x is less than 5. And now that you think about it, Chris never told you how you can take a Poisson and answer probably like the question like the probability that x is less than 5. I only gave you an equation for saying the probability that x takes on a specific value k. But some engineering student is like, oh, I know what to do. We're just going to take our good friend the for loop in mathematics, which looks like this. And we're going to for loop from I equals 0 up until 4 inclusive. And we're going to add up the probability that x equals I. So this is a very fancy way of saying take the probability that x equals 0, add it to the probability that x equals 1, add it to the probability that x equals 2, 3, 4, and then you're done. Since they're all mutually exclusive probabilities, we can just add them up. You can only do addition when your events are mutually exclusive, but assignments to a random variable are mutually exclusive events. So my solution would look like this. I define and declare to all who will listen x is a Poisson, and I have to give the parameter, which is 2. Then I say exactly this. The probability that x is less than 5 is the sum of all of these probability mass functions. And then I could just plug in this beautiful equation we derived earlier for the probability mass function of a Poisson. If x was not a Poisson, obviously I wouldn't be able to use this probability mass function. Since it is, I get all this math for free. I didn't have to derive the probability of a binomial in the limit. And then you could just plug this into a calculator, and you can get that this gives you a 95 probability of 95 that you'll get less than 5 hits within a second. Okay. Questions, comments, concerns? Yes.
So one thing that's pretty important is like when you're choosing your values, k and lambda, that they're within the same time frame, right? If k happened every 2 seconds and lambda was every like 5 seconds, it wouldn't really work.
You want to just work that through?
Yeah, you have to adjust them. But my question is, if they were the same time frame, would you like multiply them, for example? So if k was 4 hits every 2 seconds, then would the probability that x is less than 10 be the same?
Well, we'll call the k as your query.
nicely.
So what's your query? And it has to be an integer. What was your query? Oh, you want to say like k is now. You were talking about what's 4 hits within 2 seconds, right? Okay. And now you have a rate that's provided within 1 second. I could solve this using x, or let's call it y, as my Poisson. And now my y will be the number of events not in 1 second, but in 2 seconds. And in that case, what should be my rate for number of events within 2 seconds? 4. Yeah. And then you could say, what's the probability that, y equals 4? And if you worked out the probability that y equals 4, I believe it will be equivalent to if you did the probability that x took on the value 2. Well, actually, maybe those are slightly different questions. No, those are slightly. Because 4 hits within 2 seconds, it's a similar but slightly different question than 2 hits within 1 second.
Yeah.
So there will be slightly different numbers, yeah.
Okay.
But interesting thought experiment. Yeah, you could do all those things. You can ask about questions slightly outside the time frame. You just have to adjust your rate to make it work. Can I just tell you some cool stuff? So at this point, I want you guys to be thinking, where does this show up in my life? Because I don't run Uber, Pool, will I actually see this? I'd say Poisson is one of those things that people should know about but don't know about, which means that there's all these math algorithms out there waiting for somebody to just recognize that they're Poisson. And I will give you 2 examples. One's from my own life, and one's from a colleague's life. A colleague's life is certainly more interesting than mine. But my experience was, I went to a doctor and they're trying to track inflammation that I had over time. So I went to the doctor one day and they were counting number of cells and they got 4. And then I came in a few weeks later and they counted number of cells and they said, I have 5. And they said, your inflammation's gotten worse. And immediately I was like, oh, because of the same way that you can derive a Poisson over time, you can do it over space. I'll have you guys do this in a section problem. I was like, oh, as soon as you tell me that my number of inflammation cells is 4, using some math we'll learn later in class, I could infer distribution over rates, and then I can tell, I was like, okay, the probability that I've gotten worse is only like 0.56. And I could know exactly that just because of my knowledge of Poisson. And of course, it's not so useful for me in that one case, but then the doctor learned, there was this like, oh wait, we've been measuring inflammation this whole time. We didn't know that because this process is Poissonian, we can tell people, usable probabilities in addition. So anyway, small thing in my life. Maybe the more interesting thing in my colleague's life is, do you guys know Google has this photo app that lets you take photos when it's really, really dark? Has anyone used that photo app? Okay, you can be in like basically pitch black. You can put a sheet of piano music, you can take a photo, and you can read that piano music. And I don't know if you guys use old school digital cameras, but that absolutely wasn't possible. And the reason that we were able to do this very magical thing of taking photos in incredible dark is because somebody realized that the way that photons were hitting camera was coming in as a Poisson process. And because of that, they could take lots of photos and they could ameliorate some of the uncertainty in the Poisson and end up with really high resolution photos. And it was just like, oh yeah, this incredible natural phenomena leads to all these small magical things in the world. Now, none of these things have really changed the world, but it's just gorgeous how there's these small little ways that we can use math to do something tiny and magical in our worlds. So anyways, the Poisson, I think it's kind of a cool thing. That was such a random aside. Okay, I am going to give us our 2-minute pedagogical pause before we talk about probability for extreme weather. So take 2 minutes, go to the bathroom break if you need to, and we'll continue this conversation. Okay? Okay, we're going to get some real data. We're going to look at some real stuff here. I've downloaded a whole bunch of hurricane data, and we're going to think about probability of extreme weather. But before we do that, any questions? This is our chance to have a nice little conversation about our good friend Poisson. Hopefully, during that 2-minute break, you had a moment to crystallize what we've done. Like that derivation we did at the beginning is kind of a big deal because I want you to know that narrative of where the Poisson comes from. So like just knowing that beautiful derivation is a cool thing. Then knowing a Poisson, being able to recognize it and use it, that's also a cool thing. And then we had these 2 nice asides. One was expectation, the variance of Poisson, and then we also talked about the Poisson approximating a binomial. So those two nice asides. And then, of course, the most important thing is that you just get some practice with Poissons. And that's what we're going to do next. So the US has been paying attention to hurricanes for a long time, and they've been recording it since 1851. And this is a histogram that I made, and I just made it off the public data that the US reports on hurricanes within the Atlantic. So every year here is just a histogram saying that, like, in this year, this is the number of hurricanes. And if you look at it over time, you kind of get this feeling that there's more hurricanes now than there used to be. And I was just wondering, can we just dive into that and see if we can tell that story a little bit more formally than just like, hey, check out my cool graph, it goes that way. So what I'd like to do is, let's actually go to the code and let's use our computer science skills and our understanding of Poisson now to try and understand this. So here's the data that I've got for us. It's the HURDAT data. That's what they call this database of hurricanes. And every single row here is a hurricane. It tells you things like where the hurricane was, if it had a name, and it also tells you like the strength of the hurricane. So a lot of information, and importantly, it also has when the hurricane took place. So I have some code for us to use. The first thing I had to do is, we're talking about number of hurricanes within 1 year. That seems to be the random variable that I'm curious about. I have every reason to believe it's Poissonian, you know? Well, actually, the assumption that the number of hurricanes is consistent throughout your time period is violated, but you know how we talked about how the Poisson still works when you violate the assumptions mildly? It turns out hurricanes still look very, very Poissonian, even though they're a bit seasonal. So even though hurricanes are seasonal, if you think about number of hurricanes within a year, that distribution historically looks very Poissonian. So I believe it's Poissonian, I have data, and I just need to extract a single number from that data. What I need from the data is I need to know the rate. I need to know the average number of hurricanes in 1 year. And once I know that rate, that's all I need to understand the full distribution for probabilities within a time frame, which means that this code is actually pretty straightforward. So my code is going to load all the data, and then basically I'm going to loop over every year. I'm going to sum up how many hurricanes took place in my range of years, and then my rate is very simply, wait for it, number of hurricanes I counted divided by the number of years in my range. And that's the only piece of information I needed. As soon as I have this rate, I can declare, I think I have a Poisson. And I'm going to say, here's my years, here's my rate. I'm going to say X is the number of hurricanes in a year. I'm going to declare it to be a Poisson with this particular rate. And then what I have here is, I'm going to just really quickly show you how you can use a Poisson in Python. The stats package has a Poisson, and that Poisson module has a probability mass function. So you can say, I have a Poisson with this rate, call it X, and then you can say x.pmf, and you could put in 0, and it'll give you a probability that this Poisson takes on the value 0. You put pmf 1, you get the probability that it takes on a 1. In fact, to kind of illuminate this, I'm going to loop from 0 to 40. I'm going to say, what's the probability that x is 0? What's the probability that x is 1? Should we take a look? This isn't exactly solving my problem, but it's just exploring this data. Python explore hurricanes. Okay, so I'm looking at hurricanes. I looked at 115 years. In fact, I was looking at the years 1851 to 1966. That's 115 years. Over those 115 years, we saw 975 hurricanes. That leaves a rate of 8.5 hurricanes. And as soon as I see this, because I think the process seems Poissonian, I'm going to say the number of hurricanes in a year, that random variable, is going to be a Poisson with lambda equal to the rate I calculated. As soon as you do this, you inherit the probability mass function. This is just one way of expressing it. I'm going to say, this is 0 hurricanes, and this is the chance of getting 0 hurricanes. Here's 1 hurricane, chance of getting 1 hurricane, 2 hurricanes, chance of getting 2 hurricanes, based on this rate I got from historical data. Okay, which means I could start to answer questions. But the first thing maybe we should look into before we get into a more philosophical question is, was Poisson a good approximation? So I looked at my historical data. I pulled out a lambda of 8.5. That lambda of 8.5 gives me this blue distribution for the probability of 0, 1, 2, 3, so on hurricanes per year. Let's just compare that to the histogram of hurricanes per year. How many times did we see 10 hurricanes? Well, that's the orange line. How many times do we see 20 hurricanes? Because there's only 115 samples, you wouldn't expect this to be a perfect match, but that's a pretty good match. That's what it looks like when natural phenomena follows a Poisson. Like, you could have predicted that shape pretty well just by knowing the average. Even though hurricanes mildly violate the assumption of the Poisson, it's close enough that we really get a good insight from a single number. But that's not really my question. My question wasn't, what's the distribution of hurricanes? I want to know, is the distribution changing? So what I did is we calculated this rate up to 1966. Now let's take this Poisson and see how well does it predict the number of hurricanes in a year after 1966. So I looked at that data and I noticed that there's a couple of years when you start to see more than 15 hurricanes in a year. And the Poisson says that's pretty unlikely. I want to show what it could look like to make an argument that, like, oh, it looks like the distribution has changed, or what we would call shifted. What's the probability of having a year with 15 hurricanes? So if there's a year with 15 hurricanes, I'm going to say that's pretty improbable based on this Poisson. But can I quantify that? If x is number of hurricanes a year and x is a Poisson of 8.5, what's the probability of getting more than 15 hurricanes? And let's do this in the code. I want to use this code and figure out what's the probability of more than 15, or is it, yeah, more than 15 hurricanes. Oh, this says more than 15 hurricanes. So I have x, it's a Poisson. I can ask its probability mass function. That's the API you have access to. Can we use our code to calculate exactly the probability of getting 15 or more hurricanes in a year? Now, what we really should do is we should sum over all those values that satisfy greater than 15. So here's what I'm planning to do. I'm going to write a for loop. And that for loop is going to run from I equals 16, because we're not including 0 up to 15, up to infinity. I'm going to add the probability that x equals I. Why is this a bad idea? Well, it is correct. This technically is the probability of getting 16 or more hurricanes. It's probably getting 16 hurricanes plus the probability of getting 17 plus the probability of getting 18. It's correct. But why is this not going to be a fun thing to code up? Let's just try. We'll do like for I in range 16 to, is it like math.infinity? Yeah, my computer's going to get tired. Uh-oh. Wait, do we not have the ability to ask the question, what's the probability that x is greater than 15? Ah, somebody knows. Yes?
And take the complement of from 0 to 15.
Oh, the probability x is less than 15 is 1 minus the probability, sorry, that's greater than 15 is 1 minus probability that x is less than or equal to 15. And that is much easier to calculate. The probability that x is less than or equal to 15 just means I have to loop from 0 up to 16, which is, man, range is such a funny thing in Python. Okay, so here I get I, but I don't want I want the probability that x equals I. In math, we call that the probability mass function, and in Python, if I want to look at the probability mass function of I for this Poisson random variable x, I just do x.pmf. I'm going to do probability starting at 0. and I'm simply going to add up each of these probability mass functions. You know, I'm going to be doing the sum from 1 to 15. Now, I'm not supposed to report that number. I'm supposed to report 1 minus that probability. So I'm going to calculate, this is the probability of 0 to 15 hurricanes, and I want 1 minus that probability. That's the probability of more than 15. So let's run this. It says the chance of getting more than 15 hurricanes is about 1.3%. Okay. So if I go back here, I'm like, well, there's these 2 years with more than 15 hurricanes. Maybe that's believable. It seems unlikely, but within the realm of possibility. What looks less like it's in the realm of possibility is since 1966, there have been 2 years with more than 30 hurricanes. And can we calculate the probability of more than 30 hurricanes? Absolutely. We just do the exact same thing. It's just now instead of looping from 0 to 15, we're going to loop to 30. And the probability of having a year with more than 30 hurricanes, assuming the distribution that we modeled going up to 1966, is 1 minus 0.9999999, and then a bunch of 9s and then a 7. It's incredibly unlikely, the number of hurricanes that we've seen. And in fact, if I plot the data after 1966, it no longer looks like it's coming from this Poisson. In fact, it looks like it's coming from a Poisson, but a different looking Poisson, a Poisson with a much higher rate. And so this is a pretty good argument that the rate of recorded hurricanes up till 1966 looks very different from the rate of recorded hurricanes afterwards. Now, there's a lot of stories that are worth talking about. Certainly, one of the first things that should come to mind is this incredible change that has happened to our Earth. There's a lot more CO2 in the world. That means that there's a lot more heat in the atmosphere, which means a lot more energy for hurricanes. So certainly this is a hypothesis for why we think there could be a distribution shift. It turns out this has led to more extreme hurricanes, but it turns out this is not the exact answer for why there is such a big distribution shift in number of hurricanes. So more energy in the atmosphere means that when we have hurricanes, they tend to be bigger, but it doesn't necessarily mean more hurricanes. Does anyone have another hypothesis? Do you guys want to know? Okay, here's what happened. In 1966, they started using satellites to track hurricanes. And so before 1966, you would only catch a hurricane if somebody reported the hurricane. And after 1966, you would catch any hurricane that ever existed. So was there a distribution shift in recorded hurricanes? Absolutely, because we got a lot better at recording hurricanes. So it looked like there's many more hurricanes per year. So there's more extreme hurricanes because of climate change, but that distribution shift, turns out it came from satellites. Anyways, there you go. Here, I put all the Python things you might want to know. They're in the slides. Come back next time, and we're going to continue this wonderful story. Thank you guys so much. Have a wonderful rest of your week. Come back on Friday, and we will learn more cool things. Okay, have a good one.